Hello guys, my name is Balkrishna and welcome to Code with BK. So in this video, we write a Java program to check if an integer n is a prime number or not. So before we begin, it is a request to please subscribe to my channel, because out of 100 viewers, only 1 or 2 are subscribed, and a subscription is very important. So please do subscribe to my channel. So let's begin. So we have to write a Java program to check if an integer n is a prime number or not, and we will use two approaches, a brute force approach and an optimized approach. So we all know what a prime number is, but just to give a brief intro, a prime number is an integer which is divisible by 1 and itself. So if an integer n has any other factor apart from 1 and itself, then it's not a prime number, then it's a composite number. Okay, 1 is neither considered prime nor composite. Okay, so prime number examples are 2, 3, 5, 7, 11, 13, 17, 19, 23 and so on, and all these integers are only divisible by 1 and itself. And if you observe, 2 is the only even prime number. Okay, and in the end I am going to run these codes on an online judge, right? So this question basically takes a number n, integer n, and checks if it is a prime or not. Okay, so I am going to code the two methods and I am going to test them using the online judge as well in the end. Okay, so let me write the first method, static boolean is prime, that takes an integer n and returns true if this integer is a prime number, returns false if this is not a prime number. Method to check if integer n is a prime number. Okay, and using brute force approach. Okay, the idea is just to get the right return value. We do not do any kind of optimizations to it, we just want the right result. Okay, so brute force approach, straightforward. We try to find an integer I that can completely divide n apart from 1 and n itself. Okay, so I am going to iterate from 2 to less than n. Okay, and if any of these values of I is able to completely divide n, okay, I return false. Okay, percent is basically the modulus operator, and percent I returns the remainder when n is divided by I. So if n is completely divisible by I, the return value is going to be 0. So if this condition is true, we have found a value of I that completely divides n apart from 1 and n, so this is not a prime number. Finally, we return true, because for all these values of I, this was never true, so return false never happened. This was never true, it means we were not able to find any value of I that can divide n completely. Okay, so n is divisible by 1 and itself only, so it is a prime number. Okay, so let me check this for the first 50 values. So I'll say for int I equal to 1, I is less than equal to n, and I plus plus. Okay, I'll say if is prime. Okay, I'll say sysout I plus is a prime number. Okay, one comes out to be a prime number and one is not supposed to be a prime number, and this is happening because if n is 1, okay, and I starts with 2, so this loop will never run because I starts with 2 and n is 1. Okay, so in that case you will return true, so we'll have to add a separate case for 1 to return false. Okay, running this again, 2 is a prime number, 3, 5, 7, 13, 19, 23, 29, 31, 37, 43, 47. Okay, we make this till 100 and we get all the prime numbers till 100. Okay, so this is the brute force approach. We are not doing any kind of optimizations here, right? So now we write a method to check if an integer is a prime number, okay, using optimized approach. Okay, copying this, pasting this, making this is prime 1 and making this is prime 2. All right. Okay, so how do we make optimizations? The idea for the prime number remains the same. A prime number is an integer divisible by 1 and itself. So we optimize this method by taking out cases which are non-prime numbers. Okay, so first n is equal to 1 is false, n equal to 2 returns true. Now why am I doing this? Because 2 is the only even prime number. There is no other even value which is a prime number after 2, so I can safely say if n% 2 equal to 0, if this n is a even number, return false. Remove all even numbers. 2 is the only even number which is a prime number. Okay, and you can add a comment for this as well, which I added on top. 1 is neither prime nor composite. Okay, and now we try to optimize this loop. So currently this loop is on. Okay, that is running the entire length of the integer n. We run this loop till sqrtn. So I'll say int sqrtn is equal to int of math.sqrt of n, square root of n, and I'll take +1 for equality. For example, if this is 3.2, int of this is going to be 3 and +1 4. Okay, so we take the ceiling value, and instead of going till n, we go till less than equal to sqrt of n. Alright, and we are doing this because you can see there is this very standard check. Why do we check up with the square root of number divided by the number is prime? Because if a number is not prime, it can be factored into two factors a and b. Okay, now a and b can't both be greater than the square root of n, since then the product of a into b would be greater than n. Okay, and this is the reason we go till square root. Okay, so now the runtime becomes sqrt of n, which is much less than n. Alright, that is to say, if there is a value I that divides n completely, we can find it from 2 to less than sqrt of n. We don't have to go all the way to n. Alright, and this significantly reduces time. Alright, and since we have weeded out all the even numbers, I am going to start with 3, and I'm going to do plus equal to 2 because I start from 3. Okay, I don't want to take 4 because I've already taken out even numbers. So I start from 3, I do plus equal to 2, I go to 5, 7, 9, 11, 13 and so on till square root of n. Alright, so if any of these values divide n completely, I return false, otherwise finally I return true. So iterate till the square root of n. Okay, so let me run this. Okay, 2, 3, 5, 7, 11, 13, so on till 97. Okay, oh, we are using prime 1. Let's go with prime 2. You should get the same exact output and the same exact output. Okay, alright. And how do we know this one is faster? Let me just time this. So I'll say long start is equal to system dot nano time. Okay, and I'll say long end is equals to system dot nano time. Okay, so this is out. Time to check for plus n plus prime numbers using brute force. Brute force is plus end minus start plus nanoseconds. So you start with the current nano time, you check for the n prime numbers, and then you get the n nano time, and then you find the time taken by n by start. Okay, and since this is brute force, I'm going to do is prime 1, and similarly I'm going to do for is prime 2 to compare times. So I say start is already defined. Okay, go to the same value of n, do is prime 2, end is already defined using optimized approach. Okay, and for n equal to 100 you won't be seeing much of a difference, but when we increment this to say 10 to power 4, you will see the difference. So when I make n to 10,000 to compare the times, I will remove this out. Okay, because this is going to do a lot of printing. Instead I take int num primes equal to 0. Okay, I do num primes plus plus, I set num primes to 0 again, okay, before the second one, and do the same, and I add a line number of prime numbers in range 1 to plus n equal to num primes. Okay, so the number of primes by both these approaches should exactly be the same. Alright, so number of prime set is 0. Oh, num primes plus plus. Okay, alright, so the number of primes from both these methods should exactly be the same, and this will take longer time than this one because this is slower and this is faster. Okay, so let me run this. So you see, so the number of primes is 1229, 1229 same, but this one takes much more time than this one. Okay, this is much lower than this one. Okay, when I make this to 100, okay, the times won't be very comparable. They would probably be the same. Okay, so this seems like it takes more time. The difference is observed when you increment the value. So I make it 10 to power 5 now. See, the first one takes so much time and the second one takes this much time. Okay, and the number of primes are the same. Okay, all right. So I am going to use the same two approaches to solve this problem. Okay, check prime. So first I am going to copy this is prime 1. Okay, I am going to copy is prime 1. And you can say they have two set of points. The first one is from 1 to 10 to power 5. The second one is from 1 to 10 to power 12. And this is not going to run, this 10 to power 12 thing. All right, because this is very slow. All right, so let me complete the code for this. Scanner is equals to new scanner system dot in scanner dot close. Then what I do is I get the value of n is scanner dot next int, and I'll say if is prime 1. Okay, system dot out dot println. The output for n has to be yes or no. Okay, so if this is a prime, you print yes, else if this is not a prime, you print no. All right, and I'm going to check it with the value of say 7, run. Okay, yes, so I'm going to submit this. Okay, and I should get 30 points. All right, so let's see. Okay, I get a partially correct answer. All right, for the second case I do not get a correct answer because first this is very slow. Okay, and second the value of n has gone to 10 to power 12. The maximum value, just print out, maximum value an int can hold is integer dot max value. Okay, which is less than 10 to power 12, which is less than 10 to power 12 because 1 2 3 4 5 6 7 8 9. Okay, so 2.1 into 10 to power 9. Okay, so for that we change int to long. I'll say long. Okay, and I start with long to L. Okay, okay, and here also I take long instead of int. So long n is kind of next long. Okay, and I will call is prime 2 instead of is prime 1. Okay, making this is prime 2. All right, so let me run this just to check. Okay, submit again. Okay, so I get this last one accepted, which was not in the previous case. So I'm using is prime 2 and I am taking the value as a long. Okay, in is prime 2. Now to get all the cases correct, the 70 points all correct, we need this method. So I'll say this is, in this case is going to be is prime 3. Okay, long n. Okay, and I have to change integer to long because it has to hold larger integers. So I say long of xqrtn is long of this and long of 3l plus equal to 2 and percent I, right? Change all ints to long and make this to is prime 3. Now I should be able to get all the output. Let me just run to check if it's compiling correctly. Okay, submitting this, I should be able to get all the points now. I should be able to get all the points now, and you see I get all the points. Okay, so this is the method, this one. Okay, you should remember to check for prime number always. Okay, and this is a very standard method in any programming language you are coding. This is a very standard way to check. You might use inbuilt capabilities of the language, but if you want to write your own prime number function, this is one of the best. Okay, all right, so this was the solution to this problem and I hope this was helpful. So if you like this video, if you found this helpful, please subscribe to my channel. And if there was something that you did not like about this video, please just don't press the dislike button. Please also let me know in the comments what was it that you did not like about this video so that I can improve upon my further videos. And you can also let me know in the comments if there is a question you want me to solve or if there is a concept you want to discuss. Thank you.